Hello, in this video we're going to look at the root test for convergence of a series. And I'm recommending 4 background videos before you look at this because we're going to touch upon each one of these. The limit supremum and limit infimum, the geometric series, comparison test, and then I have a video on just a series of real numbers. The root test, it says this: if we have a series AN with terms non-negative, and this for all n, if we let R be the limit supremum of the nth root of AN, then our series AN converges if R is less than 1 and diverges if R is greater than 1. Now remember, R is the limit supremum. So what that means is, if we look at this for each term, so the next one would be the n plus 1th root of a to the n plus 1. And then we keep going. Those numbers are kind of going to bounce around. But if at some point we see infinitely many of a specific number, actually it could be a group of numbers, then those are all called accumulation points. And we studied that in this one. So those accumulation points, one of them is the largest. It's the supremum. And that's actually what this is. So the limit supremum of this is the largest accumulation point. And if that accumulation point, the largest accumulation point, is small enough, then the series converges. But if it's big, greater than 1, then it diverges. And that's what we're going to prove here. So let's assume that R is less than 1, and by BV1 there are only finitely many terms of the terms we're looking at. The nth root of AN are larger than R plus epsilon. Now remember, R is less than 1. And so we're going to choose an epsilon that is between R and 1. So R plus epsilon is still less than 1. And that's what we do here. So if we let R star be R plus 1, then we choose an epsilon that's kind of the half the distance between 1 and R. So that way when we add epsilon to R, which is R star, it's still less than 1. Now, since there are only finitely many terms greater than R plus epsilon, we can find, so there exists an n such that when we're greater than that capital N, every term is less than R star, right? Because there's only finitely more, so at some point that is going to end, and that's the n we want to pick, and that makes every value in the series less than R star. So if we look at the series, our original series starting at AN, and AN plus 1, AN plus 2, then based on this, we know that AN is less than R star to the nth, right? Because we take the nth power to both sides, then this is true. And for this one, it would be the n plus 1th root of a to the n. So we raise each side to the a to the, or to the n plus 1, and we get this. This is less than that, and so forth. Well, this here, the right-hand side of this, is a geometric series that converges by BV2. It's a geometric series, and R is less than 1. Now, by BV3, the comparison, test for convergence, the left-hand side must converge. If this side converges, and this is strictly smaller than that, then this must converge. But this is not our original series. But there's a theorem that says adding only finitely many terms doesn't change the convergent status. It may change what it limits to, but it doesn't change whether it converges or not. So this implies that our original series, AN, is a convergent series. Now let's look at when we assume R is greater than 1. Now by BV1, only finitely many terms of this type are less than R minus epsilon. So, and this for any epsilon. So we're going to, and we're letting R be greater than 1. So we're going to subtract off something from R that still keeps us above 1. And so if R star is R minus epsilon, then we let epsilon be half the distance between R and 1. So that way when we add, or we subtract epsilon from R, which is that limit supremum, then we're still above 1. So then there exists an n such that being greater than that n, we have every term greater than R minus epsilon, which is greater than 1. Now, by BV4, just the series of real numbers, there we prove that if the series converges, then AN must limit to 0. But the contrapositive of that is also true. If the ANs do not limit to 0, then the series can't converge, meaning it diverges. So by BV4, we know that AN diverges. Well, that's all I have for today. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.